except, so the parallelogram is always biased, except in some special cases. Now, so, let's, this is a better one, okay? So let's look at a little bit about the results or the influence of this convolution. So which means everything until the step of sampling. Now, what I can do is I can take the sink and divide the sink into two parts. So I have a convolution with the sink, okay? So I divide the sink in two parts. The first part is the influence of the main law, which I call BP. And then the others are the remaining part, okay, which I call BL. So it's like if, I take the sink and I divide the sink into two parts, the main lobe and the side lobe. Okay. Now, what is the influence of the main lobe and what is the influence of the side lobe? Now, here, okay, now this plot contains many details. You need to simple to apparently to read. Now, this plot shows that in a dashed line, there is a power spectral density, the true one. Now, when I convert the true power spectral density, you see the transition is not sharp. So this is made by a real filter, not an ideal one. Okay? So now, when I make the convolution with the main law, that means how is done the convolution? The convolution is done this way. So, I take the sink, I shift, I put in one point, and in that point, all the contribution coming from the multiplication, they are integrated and summed in that point. Okay? So this is the meaning of convolution. So that means that in this point, this frequency, where the amplitude of the true power spectral density is here, by the effect of integration. So when I integrate, I'm fixing here and summing, calculating the area which is given by that and the area that is given by the other side. Now, focusing just with the main law, in the main law, it happens that this main lobe is integrated with the true power spectral density, all these areas. So the main lobe is simply having the effect that is smoothing the transition. So the main lobe is, the effect of the main lobe is to reduce the selectivity. Okay? So the main lobe is affecting the selectivity, the transition. Okay? How fast is the filter? What is the influence on the same position about the side lobe? Now, let's put myself, okay, here. Now, if I'm here, the side lobe in a position here, look at the dashed line. The true power spectral density is 0 or approximately 0. And then I need to estimate the mean of the power spectral density. Now, the mean of the power spectral density is larger than 0. Now, why? It's because the side lobe, okay, are capturing energy from the main lobe of the power spectral density, and this power is going there. Now, this is called leaking effect or leakage effect. So, in the parallelogram is affected by smoothing, mostly due to the main lobe, and spectral leakage, mostly due to the side lobe. So the side lobe are introducing these spectral leakage. Now the spectral leakage might hide some other signal that perhaps, like there, the sinusoidal, so that perhaps I want to see. And in addition to that, you know, if the power spectral density here is 0, close to 0, or I don't know, is 60 dB less, 60 decibel less, okay? Due to the effect of these side lobe, the power spectral density that I estimated by the periodogram is not 0. Now, I was here. This is the book. I remember I made a MATLAB test on that. Okay, by the way, look at this. You know, this is the periodogram. I made a simulation, and the periodogram is this. One line. Okay. So that's the periodogram. Everything before is a preparation of the data. Okay. So now let's see this effect of a spectral leakage. Now in my simulated case, I simulated, so the dashed line is the true power spectral density plus a small sinusoid there. Okay? So if I make a periodogram, the periodogram comes out to be this. So this is the estimate of the power spectral density by the periodogram for an experiment where I add one sinusoid with 10 to the minus 6 amplitude with respect to 10 to the 0, which is exactly the 60 dB I was considering. Remember, this is power, okay? So I have a sinusoid 60 dB less, which is close to the power, to the edge of the power spectral density. The way I generate this dashed line is because I generate by the Butterworth filtering. So I took a white noise filtering, you see on the top. So that filter was a Butterworth, and the Butterworth with a high degree, very high, in such a way that, you know, I create artificially, numerically, a very strong and quick transition from the pass band of the power spectral density to the 0 or close to 0, or stop band, if you like, of the power spectral density. And so here it is. So, you know, what you see here, you see that, if I don't take any countermeasure, I don't see the sinusoid. But by the way, I don't see anything. So and by the way, you know, apparently, my spectral leakage here is so much influenced by the power spectral density, then, you know, my spectral leakage is going to 10 to the minus 4, so 40 dB less with respect to the power of the signal. And if I have a 10 to the minus 6, which is 60 decibel less of a sinusoid, whatever signal, I don't see it. Okay? So then, you know, if you want to use the periodogram to see or to spot a signal hidden into another one, like, you know, you have a transmission that is hidden into another one. You have a signaling that is hidden into another one. Now that is a security and is a so important issue. So, you know, you have another signal, you don't see it. Okay? So there is a way to do it, but, you know, we discuss. Okay? I wanted to illustrate. Now, if I make another, okay, I have another degrees of freedom. Now, let's avoid for a minute what I did. But, you know, these are different curves carried out by the periodogram with different length. So what we know from the theory is that the periodogram is asymptotically unbiased. Okay? So, you know, asymptotically unbiased means that if I take a very, very, very long sequence, then, you know, what's happened is that this bias or even this spectral leakage is going down. So this is by making the length of the sequence 128, probably 250, and until I get the 1024. Okay? Now, so what's happened here is that the sinusoid is coming out. So at a certain point, the sinusoid in this messy increasing end is pushing out. Okay? Strange behavior. Now, so you should not be surprised. And I will explain in a minute why this happened. Okay? So you need to know that when you are doing this job, or when you are starting doing this job, or when you are touching something similar related to this job, because I am 100% sure that each of you will do something that is related to that, okay? To this or to our subject. So anyway, so when you start doing this, you cannot take anything as a surprise. There is always a justification. You need to take, sit, paper, and write. Now, let's see what's happened with that sinusoid. By the way, the variance is not as big as I mentioned, and there is another reason for that. Okay? So then I tell you what I made to make such a small variance and such a good resolution, let me say, to see the sinusoid. Now, let's see what is the behavior for a sinusoid. So what I'm doing now is I take that example and I'm using the property that if I have two random processes that are uncorrelated, the power spectral density is the sum of the two power spectral densities. Okay? So I know that if I have two random processes, so imagine they have xn plus yn. Okay? These are two random processes. And then, if I do random processes and I calculate the autocorrelation, Rxk, it is the sum if they are uncorrelated. Uncorrelated is Gaussian, okay? And the power spectral density is Sx omega plus Sy omega. Okay? That's the property. Now imagine that x is that one and y is a sinusoid. So let's assume that the sinusoid is A, the amplitude, cosine omega 0 n plus random phase. Let's put the random phase. We always put so. It's not important. Okay? Now, what is the autocorrelation of a sinusoid? So, if I calculate the autocorrelation is, it is a squared divided by 2, we computed, okay, cosine omega 0 k. Okay? If you go back, we computed that. So the autocorrelation for a sinusoid with a random phase, so we are assuming that phi is uniform 0. Then our autocorrelation is behaving that way. Okay? Then what is the power spectral density? Okay, this is the same, plus it is a squared divided by 2, then it is delta omega plus minus omega 0. So it means that I have 2 delta. Okay? Divided by 4. 1 and a half. Okay? So, I have 2 delta. So this one is made by 1 delta and 1 delta. Okay? Now, let's calculate, in this case, the same steps that I calculated above. So, I'm making the periodogram for x, which is on the upper part of the board, and y is the new signal, which is a sinusoid. Now, so when I calculate the periodogram and I take the expectation, so since they are, they are statistically independent, let me say, then what I do is when I do the convolution, okay, I need to do the convolution between that combined with the sink and this combined with the sink. Okay. So, what I need to calculate is omega 0 minus omega 0 convolved circularly with the sink. Okay. So how to calculate the convolution? Convolution, it's simple, and it is minus omega 0. And then I zoom myself on omega 0. Okay? So let me zoom, so let me say, make it bigger. Okay, only for the sake of making reasoning. This is omega. So, if I have a sink and delta, the conversion, you take the sink and puts into the delta. Okay? So, my sink are here. And then I have a similar one. Okay, but I look at only one. Okay? So I put a delta here. I know that the height is n. Okay? So the value here is n times a squared divided by 4. Okay? That's for continuous form. Now, after doing that, I'm sampling. Okay? Now, up to here, everyone gets this point. Now the point is sampling. Now, I know that the spacing here is 2 pi divided by n. Okay, that's the mode of spacing. Now, let's start the sampling. Okay, so when I start the sampling, the first sample I put to 0. Then I'm sampling regularly. This is another 2 pi divided by n. That's a sampling, okay? So what's happened by the sampling? That, I get one value here, I get one value here, one value here, one value. So, even if I expect that the sinusoid is 1 delta, I get a huge amount of values. I don't have just 2 spikes. Sorry, 2 values, 2 delta. I have a combination of many others. Okay? Many others. So I have, a good setup. So now, let's see what's happened. What I expect is the following. Look at that. The spacing between the sink is 2 pi divided by n. And the spacing of sampling is 2 pi divided by n. Now, if the grid of sampling is matching the zeros, that means that my sampling would be sample here, here, then to the maximum one value, then here, here, and so on. So if the sampling matches the 0, what does it mean? It means that if omega 0 is equal to 2 pi divided by n multiplied by a certain k0 integer. So if the frequency of a sinusoid is an integer number of 2 pi divided by n, if the angular frequency, okay? Then it happens that the result is 0, 0, 0, 0, 0, except one value. Now, so if I am in this condition, this one, the results of convolution, blah, 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 as a result, it gets one sample here, and then, one sample there that is 0, one sample there that is 0, one sample there that is 0, here 0, here 0, here 0, here 0. My parallelogram is unbiased. It's not biased in this case. So, that's very good. So, we can say that for a sinusoid, if omega 0 is equal to 2 pi divided by n multiplied by k0, then the parallelogram is not biased. Now, that means that it's not biased for a sinusoid, but it is biased for the other, okay? Because here we are considering the combination of the two. Okay? So now you can understand a little bit about this plot. Why I have just one peak here, one single, because I choose the frequency in such a way, so I choose omega 0 in such a way that is a multiple of 2 pi divided by n. It's an integer multiple of that. Now, how do I make it? So let's interpret another way. The other way to interpret it is that if this situation is met, that means that within the time window represented by n samples, the sinusoid makes within n an integer number of cycles, and specifically it is k0 cycles in n samples. That's a special case, okay? So if I choose the sinusoid in such a way that within n samples it makes an integer number of cycles of the sinusoid, then my parallelogram is not biased. So this is what's happened here. Now look at here. I'm always going by power of 2. So I have a 128 over 256, 512, and then 1024. Okay? So the reason why is that, what I've been choosing a frequency of a sinusoid in such a way that within, starting from 128, it makes an integer number of cycles. Now, why the sinusoid is pulling out? It's pulling out because of this. So the peak here is dependent on n. So if I take a longer, this one is growing. Okay? And then what's happened is that magically the sinusoid is pulling out of the power spectral density of the other. So that's the reason why by increasing n, this delta is pulling out and the other is going down. So the sinusoid is going up and the flank, the side, is going down. The side is going down because it's less biased, and the sinusoid is pulling up because it's the amplitude is going up. Now usually when I am at this point, it comes out a question. There is something that doesn't work. Let me sketch better. Because I want to have this question. Because if you make me this question, you start asking yourself questions. Now, assume that I have in this case, okay? So I have, the time window n. So my data is segmented. So the length is an integer number of sinusoid. Perfect. So I'm here. So omega 0 okay, which is 2 pi divided by n multiplied by k0. So when I make the analysis of the periodogram, then it is 0, then you know I have a k equal 1, then k equal 2, k equal 3, blah blah, and then I have a k0. Then I have a k0 minus 1, and k0 plus 1. Okay, so what I have this big, and all the others are zeros. So if I calculate the bias in this case, what I get is this value, which is a squared divided by 4 multiplied by n. So that means, you know, the longer I make the window n, the bigger is the power spectral density of the sinusoid. That means that it seems that the sinusoid power is rising up. So the larger I make n, and the bigger is the power of the sinusoid, which is a nonsense. So what is the power of spectral density? It's the power watt per hertz unit. Okay? Power per hertz. Because this axis is hertz or or radians per second, it's that. Okay? And for the sinusoid it's growing in power. Possible? There's something missing here. What is missing? What is the power? The power, if the power spectral density is watt per hertz, if I want the power, what do I need? I need hertz. Okay. So how much is the hertz?
Time divided the 1 divided.
Okay. Now, so this plot, you should interpret this plot as if you have a set of baskets. Listen to me, okay? That's another point. I try to put in the book, but the book has to be nice to see, to read, what I mean. If you write these silly stuff, then since the book goes also to other colleagues, they say you were telling me stupid stuff. Okay, so listen to me. That's the reason why you need to come to lecture. Now, what is the periodogram? That's the periodogram. Okay. So the periodogram is this. You have between minus pi and pi, you have a set of baskets. And this basket, each of these baskets is collecting the power. Okay? So you have a set of here. One is here. Okay? 2 pi divided by n, another. 2 pi divided by n, another. 2 pi divided by n, another. Okay? So I calculate how much power goes in each basket. Okay? So the basket is spaced apart 2 pi divided by n. Okay? Or in normalized frequency is 1 divided by n. Because this is normalized cycles, okay? The frequency is this guy divided by 2 pi, so it's 1 over n. Okay? So in frequency, in normalized frequency technically, okay? So I put 1 here, 1 over n, put another, 1 over n, put another, and so on. And so the periodogram is calculating how much power, how much water goes in here. So, I have the signal, the random process actually, this random process is spraying water and then computing how much water goes in each bag. Okay? So the size of the bag is 2 pi divided by n, or in frequency 1 over n. So what I should do is this. This is the plot that I make by stand. But mentally you need to think that this is the corresponding power spectral density. Now, how large is this in frequency? This is large in frequency, 1 over n. What is the power? The power is power spectral density multiplied by the band of the bag. Power spectral density multiplied by the band of the gag. So it is a squared divided by 4 times n multiplied by 1 over n. So this area is always a squared divided by 4. So it's not changing. So if I increase n, what changes is that this is squeezing and this is going up. The power is not changing. It's only the way you allocate the power. Okay? So this is the reason why if I change n, it doesn't change the distribution in this area. Because there is not such an effect. So we are now facing another aspect. In a place where the power spectral density is almost constant, there is no bias. Okay. Now, this stupid aspect, is the basis. Is the concept, the fundamental concept of interpreting the periodogram as a filter bank. What is a filter bank? A filter bank is a set of filters where every filter is collecting some energy. This story of the bag actually is a filter bank. Okay? Because when I say I put a bag that is collecting water, actually what I'm doing is I'm making a band pass filter. I'm making a band pass filter which is filtering the signal and calculating the power per band. So let's see now this interpretation. So this is the true meaning of the periodogram. The periodogram is doing this way. So I have this, don't be scared, this is just a representation with a decimator of a filter bank. Okay? So a DFT makes a filter bank. What is a filter bank? It's a bank of filters. So here, look at here. I have a bank, filter here, band pass, band pass, band pass, blah blah, band pass, and band pass. Okay? The spacing in frequency of this filter is 1 over n. Or in omega is 2 pi divided by n. Okay? So that's the spacing here. Or the aperture of each band pass is 2 pi divided by n. So everybody of these filter is collecting how much power goes in this filter. And so how much power goes here is this integral. Okay? And so, the periodogram says all goes here is mapped into this bin. Now, for this reason, these are called, frequency bins. They are frequency bins because in every bin, the bin is like a rectangle. Okay, so in every bin, it goes a certain amount of power. So, this is a frequency bin, then the neighbor gets another. Now, interpreting, since every filter cannot be ideal, since every filter is real, so since every filter is not made this way, but it has some bringing, This ringing means the power that goes in this bin is taken from the outside. This is the spectral leakage. So, you know, you have interpreting the periodogram as a filter bank measuring the power. You can get the interpretation of spectral leakage. You can get the interpretation about the measuring the power and so forth. Okay? Now, the periodogram is estimating, okay, is applying a filter that is represented by here by a sink square, and the sink has a 0 and this one. That's a filter bank. Okay, so our filter bank is carried out by a set of filters where each of the filter is a sink square. So that's the bias. The bias is not the truncation. The bias is due to the fact that, you know, our bandpass filter, which is implicit in the computational periodogram, is represented by a sink square, and the sink square is due to the computation of the DFT by the periodogram. By the computation of the periodogram by the DFT. Okay. Now, so if I want to make a periodogram with a lower spectral leakage, what should I do? I should redesign this filter, each of these filters. Okay, I should make it different. Now, so how much is the, you know, how much in every DFT, how much is the behavior of this filter? Is a sinusoid, it's a piece of sinusoid. If you look at how do you decompose by the DFT, you get a piece of sinusoid. So each one is a decomposition with a piece of sinusoid. Okay. Now, what about if I want to make a filter that is smoother? Now, if I want to make a filter that is smoother, I can take, rather than a piece of sinusoid that is sharp, a piece of smoothed sinusoid. Rather than smoothing a sinusoid, I can smooth a signal. So, if rather than taking the signal as it is, I smooth the signal before entering to the DFT, then the result is that my sink filtering is smoother. So, this is another key point. So, one possible way is that rather than filtering rather than filtering by a filter bank that is represented by a sink square, I try to smooth this filter bank. But you know, it's dually obtained by smoothing the signal itself. Because the way it works is that I take the signal and then I multiply by a sinusoid. This is how you compute the DFT. The DFT is you take a block of signal and you multiply by the sinusoid with the frequency 0. You take a block of data, you multiply by a sinusoid with the frequency omega 1, omega 2, omega 3. Okay, now, so it is. So filtering is carried out in this way. So the DFT at the frequency omega k is obtained by summing of x n a minus j 2 pi divided by n multiplied by k times n. And sum n from 0 to n minus 1. This is the definition of DFT. Okay? Now, what about how to make the filter smoother? If I want to make the filter smoother, so if I want to remove the side lobe, what I should do is, rather than multiply by this sinusoid, okay, I multiply by sinusoid that is smoother. If I multiply by this smoother sinusoid, that means that I'm windowing. If I'm windowing, so that means that I need to apply here a window. But you know, applying the window to the exponential or applying the window to the data is the same. So rather than making DFT with a smoothed basis, I smooth the signal because the result is the same. So that's how the other results has been computed. The other result has been computed because I pre-multiply the signal before calculating periodogram by a Bartlett window. What is a Bartlett window? Triangle. So that means that, I pre-calculate. So the way I did is that before making the DFT, I applied here a triangular window. So, the periodogram is carried out in this way. I take the signal, I window by a triangular window, and then this goes into the conventional periodogram. Now, since I apply a triangular window to the data before the periodogram, it is working as if the basis has been smoothed. So it is working as if, the response, so the Fourier transform of a triangle is a sinc to the fourth power. Because a rectangular is a sinc square. In power, is a sinc to power 2. Okay? In power. Okay? So, if I make a triangular shape, the Fourier transform is a sinc to the power 4. And sinc to the power 4 has the beauty, if this one is a sinc square, sinc to the power 4, all the side lobes are much smaller. So I remove the side lobe. But the side lobe are those that in the frequency domain are generating spectral leakage. So I'm reducing the spectral leakage. So now I can go to the previous figure and then you can compare. So this is the conventional periodogram, okay, made with the same amount of data, which is 1024. This one. This means that I take the data and I don't window. I take the data and as it is, I compute a DFT on the data. This one is when I take the data and before computing, I smooth by an ending window. And last is when before computing, I apply a triangular window, which is called Bartlett. Okay? So by making the Bartlett, all these spectral leakage is severely reduced. It's reduced because the side lobe here is a sinc square. The side lobe here is a sinc to the fourth power. Now, when the side lobe is reduced, you see, the sinusoid comes out. I told you it's an art. And art is carried out by some rules. As these are the basic rules, okay? So, to, just to highlight in this plot. So this is carried out by the periodogram with a rectangular window. This is a Henning window, which is I take the data and it's smoothed. And Bartlett window means that the data has been, smoothed by a triangular window. Okay? That's how the data has been pre-windowed. Okay? So, calculating just to figure out, okay? Calculating, in the bias. The bias here is a sinc square, and here I calculate for a triangle because it's easy, okay? And the bias here is a sinc to the fourth power. Now, here the bias is a sinc square, and the main lobe, okay, is 2 times 2 pi divided by n. The main lobe here is a sinc to the fourth power, and the main lobe is, how much is that? So, look, the triangle is a convolution between two rectangles, but the rectangles are half of the dimension. Are half of the dimension. Since the rectangle are half of the dimension, right here, so you can meditate after. This is smaller rectangle convolved by smaller rectangle, okay? This side is n, this size is n, but this is n half. There's a convolution between two rectangles that is n half. So that means there's a sink to the fourth power, but the main law, which is reflecting to the selectivity of the system, is 2 times 2 pi divided by n divided by 2. Okay? So the main log is 2 times bigger. Okay? So you can say that here, change a strange color, okay, so here, I gain in spectral leakage and lose in selectivity. Okay, that means that my transition is smoother, is double than with the rectangular one. So, which has to be preferred? It depends. That's my basic comment. It depends. If you want to have a strong selectivity, because you know for some reason that, I don't know, selectivity is relevant, then you try to have the maximum selectivity. Then you use a rectangular one. Rectangular is the fastest selectivity. But that means that you don't need to care about the spectral leakage, okay? Which is that one. If on the other hand, you care much about spectral leakage, but you don't care much about the selectivity, then you use appropriate window. And your database of possible window, if you just check, it's huge. And so, which is better? You need to try one by one. You need to see case by case. So if you go to to any signal processing book, you can see you put the window word, even MATLAB, you put the window, okay, comes out a long list. Then you try each one. You compare the side lobe, which is reflecting the leakage. You compare, with the transition with the main lobe, and then you choose the one that is more appropriate with your case. If you don't know what to do, my recommendation is you start with the rectangular, then you go to the triangular one, okay? And then you see if the scenario from the triangular and rectangular is changing. Like here, look at here. If I make a rectangle and make a triangle, in a triangle I can see a sinusoid that I could not see before. So that means that, that sinusoid, if it is important for me, then I need to use a triangular one, okay? If for some reason the transition, you don't really see much of transition, because I try to simulate as sharp as possible, but it's not much appreciable. You cannot much appreciate. In order to see the transition quite evidently, you need to use the n samples that it should be smaller, like 128 or so. Then you will see this smooth transition. Okay. I think we are almost out of time. So we touched about the variance. We talk next time. Okay, so we have seen that about the parallelogram. We have seen the bias. Let me summarize about the variance here. So the variance, the bias, not variance, was So the bias, you know, depends on cases, and the for white process or locally or power spectral density, locally flat, okay, or if sinusoid with sinusoids with frequency integer to the number of cycles, which is omega 0 is equal to 2 pi and pi k 0. Then, you know, in all these cases, the bias is 0. So the periodogram is biased except to some cases, okay? And these are the cases where, you know, the bias is 0. And for about the window, so the bias is affecting the selectivity and is affecting the spectral leakage. Now these two are one opposite to the other. So if I want a spectral leakage, if I want to cope with the spectral leakage, then I pay in selectivity and vice versa. The way to cope with that is, so for controlling, by windowing. Before computing the periodogram. That has an implicit truncation to n samples, rectangular window. Okay. So this summarizes, you know, what we've been doing, and we conclude.